Welcome to this course on phase diagrams. This is basically a course on different types of phase diagrams and their evolution as a function of temperature, pressure and compositions. And as a part of massive open online course, you will be exposed to about 40 hours lectures on this course, and every week there will be 3 lectures followed by an assignments. So before I actually discuss about the material of the course, let me just tell you a few important aspects of the course. This is about myself. Okay, you have already seen that. So there is my email address and my website. So if you want to know details, you can check in there, you can write me emails. So what is the basic objective of this course? I know that you are from different backgrounds, different places, but basic objective remains same for all of you, to familiar with binary and the ternary phase diagrams and microstructure of different materials. So idea is to connect the microstructure of materials with phase diagram. As I have said in my introduction video, the connecting links for any material properties is the microstructure. We produce something by using different processing techniques to achieve certain properties or combination of properties, but the controlling mechanism is microstructure. So that is why you have to connect these phase diagrams with the microstructures. That is the idea. So now the outline is already open to you. Just to tell you that in a brief what we will do. First and foremost important thing in any phase diagram is what is known as phase rule and lever rule. And as I said, the prerequisite of this course is thermodynamics of the materials. So therefore we have to do some kind of a recap or recapitulation of thermodynamics of the different phase equilibrium or different thermodynamic aspects of phase equilibrium. In addition, we will do also binary, isomorphous phase diagram, eutectic, peritectic, monotectic and syntectic phase diagrams. And each of these phase diagrams will be dealt with in such a way that you get a good flavor of the basic features of the phase diagram, understanding its evolution, also understanding the microstructures. Followed by we will talk about alloy phases, that means different kind of intermetallic phases or intermediate compounds, and intermediate compound formation is governed by different rules. So we will talk about those theories, then we will talk about Hume rotary rules for solution formations, and I have also marked here that we are going to discuss about some possible solid state reaction like eutectoid, peritectoid reactions. Most importantly, the systems like iron carbon, which is the basis for steel making, nickel aluminum, which is the basis for superalloys, and other aluminides like titanium alumina or iron aluminum systems will be discussed. And those of you who are from ceramic background or who are wish to know about ceramics, we will also look at some ceramic phase diagrams like silicon dioxide, aluminum oxide, L2O3, nickel oxide, manganese oxide phase diagrams and many others. These are only examples. So that will give us a good idea of binary phase diagrams. Then we have to move into ternary, because most of the alloys of importance in this metallurgical community are ternary alloys, like stainless steel is a ternary alloy of iron, chromium and nickel. So therefore it is important to understand the ternary phase diagrams also, because you need to read this phase diagram and get an idea about how to use this phase diagram. So we talk about Gibbs triangles, isothermal sections, 2 phase equilibria, tie lines, 3 phase equilibria, and at the end we will discuss some of the multi component systems like stainless steels, high speed steels, or superalloys. This is in a nutshell the whole syllabus of this course. It will be dealt with in 40 hours time. So I just wanted to show you some of these books. It may not be available to you, but you should know some of these books are already available as open source internet, but some may not. The first one is most important book. This is known as Alloy Phase Equilibria by Alan Prince, published by LCBR Publications. It is very expensive also, not available in the many libraries. The second one is a book written by one of my own colleague, Professor Sant P. Gupta. It is very cheap, it is about 400 rupees the cost of the book one can buy. And I just like to show you the books also. This is the book by Alan Sprints, and this is the book by S.P. Gupta. You can see that this is a bigger book, but written nicely. This is a smaller book. One is to also look into some other books to read this book. And in addition, we need to, I have also given a few other things like Phase Diagrams in Metallurgy by Rines, which is a reference book. And in order to understand the microstructure, one needs to look at Physical Metallurgy Principles by Abrasian and Reedhill. It is a classic physical metallurgy book, now also available in India, very cheap, not very expensive. And to understand ternary phase diagram, I have not found any other book other than the last one, Introduction to Phase Equilibrium and Ceramic System by Hummel. Better than that book I have not yet seen. So this is the book, you can, if you can avail it, you can read it and understand. Otherwise, we will provide you, I will provide you enough material to understand the basics of this. Now with me I have two TS, and I would like to introduce both of them. They will help you, they will rather answer your questions, they will post the assignments, and they will interact with you if possible by emails or so. They are Mr. Nirmal Kumar, and the second one is Mr. Shikhar Mishra. They are all our students from IIT Kanpur, and they will be the shoulder the responsibilities of the managing the course, I guess so. The course module is will be controlled by them. I will be only giving lectures and try to make use assignments, but they will be correcting assignments, they will be grading you. So therefore you should be in touch with them. Now as far as evaluation is concerned, this is I guess very important for IIT students, also other students, because finally at the aim of this course is to get certificates from the NPTEL, is it not? So that's why we have divided into two categories. One is assignments. So every week there will be an assignment, as I said, and at the end of this course you will have an exam. So assignments will consist about 50% weightage of the whole thing, and in-sem exam will be about 50% weightage. That's good actually, because if you solve the assignments, you will be getting more benefits in the in-sem exam. Now there is a catch in it, and let me also to tell you that added benefits. There are 12 assignments in the course, because course will run for 12 weeks, and I can guarantee you the way I will share the question paper in such that 50% of the problems in this in the exam at the end will form the assignments. So if you solve the assignments properly, you can clearly see that you will get an added advantage for that. So that's why you should pay attention to it. So now with this brief introduction, I just have to now move on to the course, because each module is very small. So I have to tell you in details what I am going to teach and how I am going to teach, right? So in a course like phase diagrams, the most important thing which people comes into mind is what is a phase. As we know, phase word is it's a misnomer. For material scientist, phase means something. For electrical engineer, phase means something else. Electrical engineers tell you that 3-phase line, 2-phase line. That means there is a lag of the current or voltage sine waveforms. That's what is called phase. But for a metallurgy or material science, this is not the case. In the simplest form, phase is nothing but another term for solid, liquid or gas. That's what a novice person will understand and tell you. It is nothing but a term for solid, liquid or gas. Like I have given 3 examples. There is ice in a glass with water. In a summer day, you will take ice from the refrigerator and then put it into water and drink. So you have 2 phases of water present in it. One is solid ice, other one is water, which is liquid. Similarly, for liquids, you can see you can add oil, kerosene suppose, into water, you will get 2 layers. You have seen probably if you add kerosene into water, I could have done experiment here itself, but that is not a good idea. You can do yourself. You can put water into oil into water, oil will float. Why? Because oil does not mix with water. So we tell them these are the 2 phases separate. Now we can also have, every day we do this at home, not every day, maybe once in a week for you. Washing clothes, you create soap solutions. Soap solution will have soap bubbles. Now soap bubble is what? Air within a meniscus of liquid. So you have 2 phases, one is air, other is a liquid. So that is how actually we define. but definitions are not so straightforward. The problem comes here. So basically, according to the classical books of phase diagram, a phase is nothing but defined in such a way that it is a chemically homogeneous, physically distinct and mechanically separable portion of a material with a given chemical composition structure. Very difficult to remember, very difficult to remember for any new student. First of all, there are three things: chemically homogeneous, physically distinct. Water is chemically homogeneous, physically distinct, you can see water, and mechanically separable from ice. You can easily separate it from ice, take it out from ice very easily, and it has a very well defined composition H2O and very well defined structure. Water is basically liquid. So therefore, we differentiate phases like this. For solids, we always tell a phase which is chemically and structurally distinct. I will describe in details. Liquids, I have already given you the example of, while in water, miscibility defines the phase. If two liquids are miscible, we call them one phase. Like suppose I add, in coffee I add milk, they get mixed together. So we call it one phase, we do not call them a separate phase. But if I add while in water, it is an immiscible system, so I have to call both of them as a separate phase. While it is a one phase, water is another phase. So therefore, for liquids, the fact which differentiate different phases is the miscibility. Gases, there is no distinction, always single phase, whether it is air, the nitrogen or mixture of nitrogen and argon, whatever, it is a single phase. So the problem basically comes for you guys on for solids and liquids. Let us first see examples, then it will be clear to you. How many phases are present in each of these? Okay, let us first take sand and salt. Both are solid, sand and salt, but if you put it together, they will never mix. So therefore, there are two separate phases. Milk and coffee, both will mix very nicely. So therefore, I put milk in coffee or coffee in milk, single phase. They are not two phases. But if I suppose again same thing, if I add sugar into coffee, sugar will mix atomistically nicely with coffee. There is no problem, that is why we drink coffee with sugar, we like it. So that means coffee and sugar is a miscible system, so therefore there is single phase. Salt and water, same story, salt mixed nicely with water, there was single phase. Oxygen, nitrogen, I said you gases, all the gases always single phase. Kerosene and alcohol, they do not mix each other. So therefore, they are two separate phases. So you got to understand that for liquids, kerosene and alcohol does not mix each other, that is why they are separate phases. Miscibility is the most important aspect. For solids, sand and salt, they are distinct, different crystal structures, different type of material, different phases. But gases, any mixture of gases we call a single phase. I hope it is clear to you now. Now difficulty comes when you talk about metals and alloys. That is what the most difficult things comes. Let us talk about metal like iron, because iron is a God's gift. Okay, it is the basic thing for steels. Steel contains about more than 99% carbon most of the cases. Iron, if you look at iron as a metal, at room temperature is as a magnetic BCC iron. That is what I have said, alpha iron. You can see on the picture, alpha iron is stable up to 910 degrees Celsius. If I heat it beyond 910, it will transform to FCC gamma iron. Okay, anybody who knows about iron, they will know about it, I do not need to explain in detail. But this gamma iron is also not stable till melting temperature. If you heat beyond 1394, this will transform into another BCC type iron called delta iron. So in each of these, alpha has a BCC structure with a different lattice parameter, gamma has FCC structure with different lattice parameter, delta also has a BCC structure but with a different lattice parameter than alpha. So each of these called separate phases. So now by looking at this, you will understand alpha, gamma, delta. The Greek letters are always used for designating phases in the books. All the Greek letters, starting from alpha to the end Greek letter, all of them can be used. Now in this case, you have three different phases of iron, because they have different crystal structures, they are distinctly different from each other. But one of the Greek letter is missing, beta. It seems beta iron is not stable at normal atmospheric pressure, that is stable at a very high pressure. So that is why this particular thing which is known as polymorphism of iron, we only write 3 phases in the iron. Now if I consider an alloy, let us take an example very simply, a steel iron carbon alloy. We add carbon into iron, we get steels, that is what we understand. Now if I look at steel, this is what we will get. This is the first time I am showing a microstructure. You see the microstructure here, microstructure shows you very nice kind of a structure with a lamella, okay, to a 2-dimensional picture, and I have marked white lamellae or white thing is alpha iron and black one is Fe3C. It is very simple to understand. Suppose if you ask any chemist, if I add carbon into iron, any metal, it will form carbides. So this is not an exception also. So here you see carbon forms carbide and the other phase of iron, which is the solid, the white one remains alpha iron. So we call these alpha iron has a different crystal structure than Fe3C. Fe3C has a complex orthorhombic crystal structure. So therefore these two are separate phases. So what you understand from this discussion is that in solids is the crystal structure and composition which makes the different phases. If these two are changing from one to other, we have to call them separate phases. That is the take home message you should take from this discussion. Okay, I hope enough is told to you about phases. Now question is diagrams. Phase diagrams are actually equilibrium diagrams. Equilibrium, what is the meaning of equilibrium? Or sometimes people call equilibria. The equilibria is nothing but a plural of equilibrium in English. Equilibrium is a fundamental concept for any branch of engineering. But you know, equilibrium has 3 things. If you carefully look at it, first thing is the mechanical equilibrium, then thermal, and last one is known as chemical equilibrium. Thermodynamically, this is very important for all the students of metallurgy. Thermodynamically, any system is said to be in equilibrium when it is under mechanical, thermal and chemical equilibrium. All the 3 equilibrium must be satisfied. So what is mechanical equilibrium? Obvious question is this. Well, okay, so let us now discuss the matchbox analogy of equilibrium, mechanical equilibrium. You know, in a matchbox there are 6 phases. If you can take the matchbox with you and check, there are 6 phases, 2 wide phases and 4 small phases. Now if I take the matchbox and keep it like this first one where I have marked it, that is the wide phase down, then we call this kind of configuration as equilibrium, mechanical equilibrium configuration. Why? Because in this configuration the potential and the kinetic energy of all the atoms in the matchbox is at the minimum. That is why it is called equilibrium. You cannot reduce the energy system less than that. Now if I take the matchbox and put it like the third case, okay, you can see it here. Here I put it on the small phase. Now energy of the system is higher than the first one because its height is also higher. So that is why this is called metastable equilibrium. Why it is called metastable equilibrium? It is very simple. You can take the matchbox in this position and just give a tap, it will fall back to the white phase. That is why it is called metastable equilibrium. It is an equilibrium but metastable. Now we can keep the matchbox like this one here, where it is kept on one of the edge of the box. Now if I leave it in this, it will immediately fall. So that is why it is called unstable equilibrium. Remember, this is also equilibrium but unstable. This is different from instability. Instability is not same as unstable equilibrium. We will discuss in next slide. So now this is what is called energy landscape. For any equilibrium, mechanical equilibrium, you can understand using energy landscape. I can plot energy of the system versus coordinate. That is what is done in this slide. You can clearly see the different curves telling you equilibrium, metastable equilibrium, unstable equilibrium and unstable or unstable situation, whatever you can call. Now in equilibrium condition, if I put a ball on this kind of a system, the ball will simply roll and fall onto the lowest position. That is the lowest energy configuration for the ball in this energy landscape. That is why it is called global equilibrium, or equilibrium means global minimum energy. Now in a system you can also have, other than this global minima, you can also have a minima, local minima like this one here. So if the ball is allowed to fall from the top, instead of running down directly to this global minimum, it can reside momentarily on the local minima, and in this situation we call as a metastable equilibrium. This is very important concept in steels, because steel is a metastable material, not a stable material. That is what we will see later on when we discuss phase diagrams. Now unstable equilibrium is nothing but you can invert this first picture and put the ball on the top of this configuration. Then obviously if I put the ball will simply fall back down this gradient or down these slopes, and there is, it's called it unstable equilibrium. Now what is unstable? In all these three situations, energy is not getting dissipated. But suppose if you are rolling down on a hill, you are going on a hill and then you have got slided and rolling down on a hill. So while you are rolling down, you are continuously dissipating energy. That is not equilibrium situation. That is called unstable or unstable situation, in which energy is continually getting dissipated. There is no balance of energy. So that is why we do not discuss, this is not purview of this course, we will not discuss on this issue, this is a separate part of thermodynamics, so that is not part of this course, but if you are interested there are books on this also available. So I have discussed you what is phase, what is equilibrium, and what is a phase diagram then, because phase diagram is what is what you will study in this course. Phase diagram is nothing but which indicates phase and present at a particular temperature, pressure and composition. This is a chart or diagram which will tell you different phases in equilibrium with each other present at a given temperature, pressure or composition. So nothing but a common way to represent the various phases of a substance and coordinate conditions under which each of these phases exist. So like this, let us take this one, the left diagram, this one, which is a phase diagram of iron as a function of temperature and pressure, because iron is a pure component. So therefore there will be two variables, only temperature and pressure, composition is fixed. You can clearly see BCC alpha iron is stable, okay, to a certain pressure like about 20 gigapascal, beyond which beta iron is present, beta iron is stable. So that is what people say, if you dig earth and go to the bottom, before the liquid iron comes, you will have ACP iron present at a high pressure. Now if you heat it up beyond our 910 degrees Celsius, which is nothing but 900 plus 273, so nothing but 1183 degrees Celsius temperature. At that temperature, BCC iron, alpha iron will transform to gamma iron. That is what you see here, and gamma iron is FCC iron, it is very stable for temperature, pressure, wide temperature, pressure regime. But when it heated up beyond certain temperature, gamma iron again will transform to delta iron, and at 1539 degrees Celsius temperature, delta iron melts to liquid. So this is what is the phase diagram of iron, and I can use this for many purposes which I will discuss when I go along. For an alloy, this is simplest possible phase diagram between copper and nickel. Temperature, composition, you can see pressure is not there because we have removed the pressure axis to look it nice. And this phase diagram has three zones, liquid, alpha and liquid plus alpha. Very clearly three zones are there. So at the end I would like to say that phase diagram is not only a unique feature of metallurgy, it is used in food industry extensively. There are books like this one by Clark on science of ice cream, and you can see this is a phase diagram from ice cream, temperature versus sucrose concentration, and how ice cream is made. That is a really big invention for human. So we are going to discuss this more. So that I would like to say this is not too bad, I guess you will understand. So you will understand as you see go along the course, you will understand more. So therefore please do not run away, we will make this more interesting.